In today's lesson, we are going to be looking at transformations of quadratics. So this is going to be a summary based on the Desmos investigation that you would have done previously in class. We're just going to summarize what you should have found. So the general form for when we're looking at transformations with quadratics is going to be f at x equals a, x minus h squared plus k. So we more commonly know this as vertex form, but this is the form that we're going to look at when we're dealing with transformations. So the first one we're going to look at is the a value. So through our Desmos investigation, you would have looked at the following graphs, right? Our first one that we typed in, y equals x squared, or f at x equals x squared. This is our main graph. So how do the values in the other graphs change, or how do the other graphs change? Right? How is the blue graph different from the red? How is the green different? How is the purple one different? Right? And the only thing we're changing in these equations is the a value. Right? So looking at how these other graphs change or transform from the red one should give us an indication of what this a value does in terms of transformations. And what we find is the a value, when a is greater than 1, we have what is called a vertical stretch. So you can imagine grabbing both parts, or the top and the bottom of the parabola, and just pulling it or stretching it, and essentially we're making it look narrow. So you can imagine if this is our regular parabola, when we make a vertical stretch, it looks something like that. When a is between 0 and 1, so a fraction or a decimal value, we have what is called a vertical compression. You can think of it getting wider, right? Again, grabbing on top and the bottom of the parabola and pressing down or compressing it to make it wider. So if this is our parabola, when we compress it, it makes it wider. When a is negative, we have what is called a reflection in the x-axis. Now, this is the technical term. You can just also say it's flipped. Right? We flipped our graph. So if it was opening up like this originally, then negative a value, it opens down or flips down. The next one we're going to look at is the h value. So again, this one might be more obvious. We have our red original graph in the middle, and then we've changed it or adjusted it by changing the h value. So we can see the green and the blue graph, and we see how it's changed. So in this case, when h is positive, we have what is called horizontal translation right, because we're going in the right direction. You could also just say it shifts right. So we're moving our graph to the right. When h is negative, you could say we have a horizontal translation left in the negative direction. And then again, you could just simply say shifts left. Now, one thing to note, the h value is opposite of what you see in the equation. It's similar to the vertex form when we've dealt with it, similar to the factored form when looking at the x-intercepts. The h value is negative because the general form has a subtraction in it to begin with. So if we see a negative in the equation, that means the h value is positive. If we see a positive, it means the h value is negative. So just one thing to keep in mind. If we look at the k value, again, the red graph is our original graph. We can see how the blue and the green one have changed. Again, this one should be a little bit more obvious than some of the other ones. So when k is positive, we have what we call a vertical translation up or you could just say shifts up. K, vertical translation down, or just shifts down. So those are what the three different values tell us in terms of how our graph transforms from the original graph. One thing to keep in mind, every transformation we were doing was coming from the base form, or we were starting with this base form and then making the transformations necessary, right? So again, depending on whether we're looking at the base form in a table, in an equation, or as a graph, right, we just want to be aware of what the base form is, because if we know what that base form is, it'll be easier to determine what the transformations are. So we're just going to go through a couple examples. So we want to describe the transformation of the following graphs from f at x equals x squared, from that base form. So if I look at the first one, g at x equals negative 3x squared, I just want to recognize what values or what variables am I dealing with. I'm going to write the general form for our transformations on the bottom so they can help me identify what variables or what values I have. In this case, in A, I have an A value of negative 3. So that negative 3 is telling me that I'm flipped, or reflection in the x-axis. But just to keep it simple, it's flipped. And 3 tells me I have a vertical stretch by a factor of 3. So my graph will be flipped and stretched by a factor of 3. For B, again, looking at my general form, seeing what values I have an H value of negative 4, remember opposite of what we see, and a K value of negative 3. So the H value tells me horizontal translation. So I could say horizontal translation left 4, or just to make it easier, shifts left 4, and then the K value shifts down 3 because of the negative 3. Looking at two more, again, same idea. Look for that A, H, and K, see what we have. So in this case, our A value is a negative, or negative 1. Our H value, we don't have 1. And our K value is plus 6, or positive 6. So the A value, in this case, it tells us it's flipped. Because A is 1, that is part of our base form. Right? So the 1 doesn't make any change. So let's actually go back to our base form and make note of that. So for our base form, our A value is 1. In our general form, the A value is 1. So if I see a 1, there's not going to be any change, or it's not indicating any change. Our H value is 0, and our K value is 0. So those are all the those are what the variables are for the base form. So if we see any deviation from those numbers, it means that we have a transformation. So coming back to C, again, the negative tells us it's flipped. The 1 is part of the original, or part of the base form, so there is no stretch or compression. The K value, though, is different. It's 6. That means it shifts up 6. And for D, again, same idea. Find those different values. 0.25 for A. H is positive 3, and K is positive 7. So in this case, we have a vertical compression by a factor of 0.25. Our H value of 3 tells us it shifts right 3. And our K value of 7 tells us it shifts up 7. So those are the transformations for this quadratic. Next, we're just going to kind of do the reverse. We're going to go from the actual transformations to figure out what is the equation. So it's going to be very similar to what we just did, just kind of going in reverse. Right? So the vertical translation of up 3 units, this is referring to our k value. This means k is positive 3. Our horizontal translation left 5 units, this is referring to h, meaning left is negative, so negative 5. Again, I'm going to write my general form down on the first one, just so I have something to remember. And all I'm going to do is I'm going to take those values and plug them into the specific parts. So I would have f at x equals x plus 5, because remember, if it's originally a minus, so x minus negative 5, that just becomes x plus 5 squared, and then plus 3. I could write a 1 in for the a value, but because it's not going to really change anything, I can just leave it. For b, reflection in the x-axis. So that refers to our a value. Because there's a reflection in the x-axis, that tells us that a is going to be negative. The vertical stretch by a factor of 2, that also refers to the a value and tells us that the value of a is going to be 2. So 2 different transformations, both referring to the a value, makes it really easy to write the equation because all I have to do is fill in one spot. So negative 2 x squared. So it's flipped and then stretched by a factor of 2. Again, same idea. Vertical translation down 4 units. So vertical translation is talking about the k value. So down 4 means minus 4. Horizontal translation, our h value, right 2 units means positive 2. The other two transformations are referring to our a value. The reflection tells us it's negative. The vertical compression by a factor of 0.25 tells us what the value is. Now I have enough information, or I've figured out all my transformations. I'm going to put those values into that general form. So negative 0.25 x minus 2 squared minus 4. And that is our general form. Or not our general form, the equation for our quadratic function with those transformations. For d, again, same idea. Vertical translation up 8 units means a k value of 8. Vertical compression by a factor of 0.5 means an a value of 0.5. Plug those two values into our general form for the quadratic. So 0.5 x squared plus 8. And that would be our equation. What we're going to do next we're going to figure out how to determine the transformations and the equation for our graph, or from a graph. Now, the one thing we want to keep in mind, we want to remember what the base form is. In this case, the base form started with the vertex at 0, 0. So an easy way to see most of your transformations is to look and see how your vertex has changed from that original form, or from that base form. So I see my new vertex here. I can write down the coordinates if I want, 1, 1. So my transformed quadratic, because I have the new vertex of 1, 1 moving from the original 0, 0, this means I've gone right 1 and up 1. So I know an h and a k value. I can now look for the a value. And for the a value, I'm just going to move this off to the side a bit. The a value, what we do is we look for the step pattern. Going back to the vertex form, A represented the step pattern. We're going to check for that. So in this case, start at my vertex, I go over 1, and then I go up my first step, which in this case is 1. I go over 1 again, up 3. Over 1 again, up 5. So this has a step pattern of 1, 3, 5. Because it has that step pattern, that's the same as my original step pattern. So there's no change to the A value. Now, you could look at all 3 values or all 3 steps, but realistically, all you really need to focus on is just this first step. If you just look at the first step, and if it's any value other than 1, then we know we have a new A value. But right now, the only transformations we have is that we've shifted right 1, and we've shifted up 1. So shifts right 1, shifts up 1. So that means that in our new equation, we have x minus 1 squared plus 1. Essentially, what we're doing by looking at the graph is just trying to come up with the vertex form for the equation, similar to what we've done before, but now we're kind of applying transformations to it. If we look at the next one, right, again, look for that vertex where it originally is, look for that new one, and see how has it changed. Right, so again, our vertex from the original one is 0, 0. If it helps to remind us, we can write an A value of 1. For our new graph, our vertex is -3, -5. So that tells us that we shift left 3, and our graph shifts down 5. So we know an H and a K value. What we're going to do now is we're going to check to see if we have a new step pattern. So we start at a vertex on our graph. We go over 1. Remember, it's always over 1. Whether you go left or right doesn't matter because it's symmetrical. So we've gone over 1. We go up 2. So we have a different step pattern right off the bat. We have the first step is 2. So this means we have a vertical stretch by a factor of 2. We have a vertical stretch by a factor of 2 because that A value is 2. If that A value was 1, there'd be no stretch or compression. If that A value was a fraction, there would be a compression. So again, just looking at the step pattern, looking at that first step, recognizing that that tells us the A value, and then seeing does it indicate a transformation. Now we have values for all 3 variables where we found all our transformations. So it would be f of x equals 2 times x plus 3, because it's the opposite of what we see, squared, and then the k value is exactly as we see it, so minus 5. And that is our equation for this quadratic function based off of the transformations. Lastly, the last example, we're going to go through and do the same thing. Find our original vertex at 0, 0. I just like putting it there just because it helps me remember. Find our new vertex. In this case, the vertex is -2, -2. So that tells me that our graph shifts down 2 and shifts left 2 based off that original. Now, we can clearly see that our graph has flipped. So that is a transformation we want to take into account. And I'm going to check the step pattern. So the first thing we can do, start at our vertex, go over 1. In this case, we're going down 1. So that means our first step is -1. Again, that's all I really need to do to be able to determine what my A value will be. Now we've already accounted for the negative because we see that it's flipped. So we're looking at just the value. The value is 1, so that means that we are going to be following the same step pattern as our base form. So the A value itself isn't going to change, just the sign. So f at x equals negative. You could put -1 if you wanted to. X minus -2. So in this case, x plus 2. Again, opposite of what you see. And then shifts down 2. So negative x plus 2 squared minus 2. So the main thing from this lesson is just, again, summarizing the Desmos investigation that hopefully you did, understanding the what each variable or value in the general form of our quadratic, what changes it causes in terms of transformations, and then how to determine the equation or determine the transformations given a variety of different representations. Whether we're given the transformations in words, we're given the equation, or we're given a graph, hopefully we're able to, again, determine the transformations and the equations.